So for this first one, it says find dy dx on the curve e to the 3x equals sine of y minus 8y. So for dy dx in terms of both x and y. So this is implicit differentiation. So when we do implicit differentiation, it's going to be like pretty similar to normal differentiation, but when we take a derivative of y, we'll put a dy dx on it. So go and take our derivative. Derivative of e to the 3x, well, anything involving e, you'll just keep itself. But we have to multiply times the derivative of an inside because it's just not a normal e to the x. So it's going to be times 3. It's going to equal derivative of sine of y is going to be cosine of y. But there's a y involved, so we'll add a dy dx. Derivative of a minus 8y is just going to be minus 8, but there's a y involved, so we'll put dy dx. And now we got to solve this for dy dx. So, just to put that, I have two dy dx's on this side. What I'm going to do is I'm going to pull those out front. And what I'm left with is cosine of y minus 8. And now I can just divide by that. So we'll get 3e to the 3x over cosine of y minus 8. And that's going to be our dy dx. Okay, so this one is a 20-point problem. So this one's one of the really big ones on this. It gives us that one boat is approaching a dock from the west at a constant speed of 20 kilometers per hour. I'm going to try and draw this. So we have some dock. We have a boat way out to the west. It's approaching it. It's going towards it. It's moving 20 kilometers per hour. Okay. At 12 o'clock, it is 60 kilometers directly west. So I'll put a little line here. That's 60 kilometers at 12. Okay. Another boat leaves the same dock at 11. So this boat leaves at 11. It's traveling directly north. And it's moving at a speed of 15 kilometers per hour. The question is, at what rate in kilometers per hour is the distance between the boats changing at 1 p.m.? So what we're trying to do is we're looking for the distance between the boats, and specifically the rate, how the rate is changing. So I'll call this lowercase d for the distance. And so I need to figure out a way to describe this distance in terms of this, because I know the speed of that, and this, because I know the speed of that. Well, if I look at this, I kind of have a triangle going on. So I'm going to give each of these sides a name. I'll call this one x. I'll call this one y. And I know that d squared is going to be x squared plus y squared. Okay, well, when we're trying to find related rates, what we're going to have to do is we're going to have to take a derivative. And every time we take a derivative, we'll do it with a d dt on everything. So I'm going to go and take my derivative here, because I've got my things connected, and I'll figure out what I need to plug into everything in a second. So first, take a derivative of d squared. I get 2d times dd dt. It's going to be 2x times dx dt plus 2y times dy dt. And I'm trying to figure out the rate of the distance, so I'm looking for this one. So I'll divide each side by 2d. On the right side, all the 2's will cancel, so x times dx dt plus y times dy dt over d. Okay. Now we need to figure out what x, y, and d and dx dt and dy dt are. Well, dx dt, we can figure that one out pretty quick. It's this, how is this distance changing? Well, it's moving 20 kilometers an hour. So it's tempting to put 20, but the thing is, x is the distance to the dock. That's shrinking, because this boat's getting closer and getting closer. So it's changing as negative 20. dy dt, well, that boat's leaving the dock, so that's going to be growing, and that's going to be 15. Well, what about x and y? And then d. Because once we have those, we can figure out what d is. Well, x and y, we're looking at this at 1 p.m. That's the big thing. That's the moment that we're looking at it. So if we know that this boat was 60 kilometers away at 12, well, at 1 p.m., it's moved another 20 kilometers because it's moving 20 kilometers every hour. They're getting closer. So that means x at 1 is going to be, that distance is shrinking, so it'll be 20 kilometers closer. So we'll say it's 40. Okay, well, this boat leaves at 11. So to go to 1, that is 2 hours later. If you're moving 50 kilometers an hour for 2 hours, that is 30 kilometers. Put my units with these. Kilometers per hour. Okay, so we have x dx dt, y, and dy dt. Well, d, we said earlier, was d squared is going to be x squared plus y squared. And if we know that x is 40 and y is 30, well, then we can go ahead and figure out what d is. 40 squared is, sorry, I think about this. It's going to be what? 1,600. And 30 squared is going to be 900. Yeah. So we add those together. That means that d squared is 2,500. And we take a square root of that. That is going to be 50. So now we know everything. I can plug that in my equation. So it means dd dt is going to be our x, which is 40, times minus 20, plus our y, which is 30, times 15, over 50. So it's going to minus 800, plus 450, over 50. So that's going to be minus 350 over 50, which is minus 7, and that's a speed, so it's being kilometers per hour. So dd dt is, I'll just rewrite it one more time without the little middle step, is negative 7 kilometers per hour, aka the boats are getting 7 kilometers closer per hour at the instant of 1 p.m. That speed might be changing as if we were looking somewhere else, but at that moment, they're getting closer to each other at about 7 kilometers per hour. Okay, so for this problem, it says, I wanted to kind of draw our picture again. Refer to the same context in problem 6. What is the minimum distance between the boats after 12 p.m.? So first, let's think about where these are at 12 p.m. So from the previous one, we are given that this one is 60 kilometers, which I'm not going to plug that in yet. I'm just noting that. And this one says it left at 11 a.m., so this is going to be at 12. This one is going to be 15 kilometers. And that's going to be our y. That would be our x kilometers. Okay. So what we got to do is going to figure out what is the minimum distance between these boats. Well, we're going to do our d squared equals x squared plus y squared. But here's the thing. We're going to need to figure out how x is changing with respect to time. So I need to figure out an equation for x involving t. And so it's going to be something involving a t, but what are we doing with the t? Exactly how we're going to involve it, that's unclear. So let's think about this. X starts at 60 kilometers away. Every 1 hour, and we're going to say t is in hours, that's going to become 20 kilometers closer. So the distance is going to start at 60 in every hour. So every time t goes up by 1, we're going to get 20 kilometers closer. So x is going to be 60 minus 20t. This also tells us that we're going to say t is going to be time in hours after 12. Because we're saying that t0 is going to be where they are at 12 p.m. And because we know that this, like x can't be negative. We're not going to eventually be a negative distance, right? Eventually this boat's going to get closer, it's going to get closer, it's going to stop. That means the biggest t can be is 3. So I'm going to go ahead and say that it's going to be somewhere between 0 and 3. If this boat moves for more than 3 hours, it'll end up somewhere over here. And that doesn't make any sense. For y, well, y starts at the 15 kilometers away from the dock. It's going to be moving at 15 kilometers per hour. So when t is 0, we ignore that, and it's just, oh, it's 15. But for every hour after, we're going to add another 15 kilometers. So that means that d squared is going to be 60 minus 20t squared plus 15 plus 15t squared. And we can go ahead and we can square those out. So d squared is going to be 3,600, 2,400 t plus 400 t squared. And we square the other one out, we'll get 225 plus 450t plus 225 t squared. And I can go in and group some of this together. So d squared is going to be 3,825 minus 1,950t plus 625 t squared. And I'm just going to go ahead and solve this one for d. So it means that d is going to be the square root of, I'm just going to put the t squareds in the front. And to make this a little bit easier for myself, I'll go ahead and I'll write the square root as instead as a 1/2 power. They're the same thing. So when I take my derivative, I'm trying to minimize the distance between them. So we'll take our derivative and we'll set it equal to 0 and we'll solve. This is optimization if I haven't mentioned that before. Take my derivative, so that means that d prime is going to be 1/2. This is a chain rule. We have an inside and an outside function, so we're going to derive the outside. We'll bring the 1/2 down. We'll keep our inside the exact same. We'll reduce our power by 1. 1/2 minus 1 is going to be negative 1/2. Times the derivative of our inside, which is going to be 1250t minus 1950. I'm going to go ahead and I'm going to set it equal to 0. Also, when I do that, rewrite this as a fraction. So I'll say this is 1250t minus 1950. And I'll put the 1/2 as a 2 on the bottom. In this negative 1/2 power, I'll say over that to the positive 1/2. So because this equals 0, that means that we can just take this part and set that equal to 0. In other words, when you have something divided by 0, or sorry, let me rephrase that. When you have something divided by something else and it equals 0, the top has to be 0. Because if the bottom was 0, then we'd be undefined. So that means 0 will have to be 1250t minus 1950. So that means that 1950 equals 1250t. So 1950 over 1250 will be our t value, which is approximately 1.56 hours. So the question is, what is the minimum distance between the two boats after 12 p.m.? Well, it's going to occur here, but we're not solving for the time. We're solving for what is the distance. So what we're going to do is we're going to plug that into our distance equation. So that our minimum distance is going to be 625 times 1.56 squared minus 1,950 times 1.56 plus 3,825, all to the 1/2, which whenever we do that, what we're going to get is, well, when I plugged it in, like using the fractions, I actually got exactly, like instead of 1.56, I did 1,950 over 1,250. I got that this is going to be exactly 48 kilometers. So that's going to be our answer. To verify it, I want to make sure that was a minimum, because maybe that was a maximum. Maybe it's like a trick question, and it's like one of the endpoints. So what I'm going to do is I'm going to check all my endpoints and see like which one was like the minimum over that. So that was my only critical point. Check our endpoints though. So if we plug in 0 times 0 squared minus 1950 times 0 plus 3,825 to the 1/2. Well, what we're going to get is just 3,825 to the 1/2, which is about 61.8, which that's definitely not a minimum, because we already know that our critical points can be less than that. If we plug in 3, what we should get is about 60, and that's also not going to be a critical point. So that means that not critical point. That's not going to be a minimum. So we got our critical point from, we took our derivative, we set it equal to 0, and we checked our endpoints 0 and 3 for our time, which I explained how we got those earlier, and our critical point. And our critical point ended up being the minimum. So I'll zoom out so you can see everything that we did. That is it for this one. Thanks for watching. Make sure, I guess, we're going to do another one for the final, so go ahead and subscribe if you want to make sure that you see that, hit the bell icon to be notified. But thanks, and good luck on your exam. I hope you do well.